So a ball is released from rest from the 20th floor of the building. Let's draw a little building right here. And then here's the 20th floor. After 1 second, the ball has fallen 1 floor such that it is directly outside the 19th window. The floors are evenly spaced. Assume air resistance is negligible. What is the number of floors the ball would fall in 3 seconds after it is released from the 20th floor? So they give us 2 scenarios, so that means I'm going to draw 2 pictures. So if I draw 2 pictures, that means I should have 2 toolboxes. Okay, so in the first scenario, the ball drops in 1 second to the 19th floor. And this is in 1 second, so time equals 1 second. The second scenario, time equals 3 seconds, but we don't know where it goes. So that means I need 2 toolboxes, so why not, v naught, acceleration time, and then why not, v naught, acceleration time. So if I were to fill out the first one, I want to say that my units are not going to be in meters, they're going to be in floors. So in my initial position is going to be 20 floors. My final position is going to be 19th floor. So I go from the 20th floor to the 19th floor. And then my initial velocity, since the ball is being released from rest, that means initial velocity is 0. So it'd be 0. Final velocity, we don't know that. Acceleration, most students would say, oh, it would be 9.81. But it's actually not going to be that because 9.81 is meters per second squared. So that means I can't use acceleration, and I don't have a value that I can just go to for acceleration. And then my time is 1 second. And then my second scenario, let's go ahead and fill that in. Initial velocity is going to be 0 floors per second. Acceleration, we don't know that. Time is going to be 3 seconds. We start at the 20th floor. We don't know where we end up to. We don't know our final velocity. So what we're going to do from here. So we have 3 equations to choose from, but I'm going to use the equation that accounts for my position, my velocity, and acceleration. So it's going to be this equation here. So if I use this equation, I just plug everything in. V naught is 0, so therefore that's going to equal 0 plus 1/2 of acceleration times squared. So we subtract 20 on both sides. -1, we're solving for acceleration. Acceleration will end up being -2 floors per second. So now that we have -2 floors per second squared, we can use another one of the same uniformly accelerated motion equations. Okay, so it's the same equation, but this is going to be for this data over here. So our second scenario. So in our second scenario, we're going to be flying from the 20th floor, so that's our initial position. We don't have initial velocity because the ball starts from rest. And this time, we do know the acceleration at which the ball will fall from the roof. Mind you, again, it's not 9.81. Time is going to be 3 seconds squared. We're trying to solve for our final position. So at what floor will the ball fall to? And we have 20 minus, these 2's cancel out, 9. And then we will end up having the ball fall to the 11th floor. So if it's falling to the 11th floor, as you see here, that means it's going to go from 20 to 11. So then the ball will fall 9 floors. And 9 floors is going to be falling into letter C from 7 to 10 floors. Going on to this next question, question number 2, we have 2 balls. One ball is going to be in free fall, release directly downwards. One is going to be rolling off the table, so it'll follow a projectile motion. Whee! And whee! So something like that. So let's go ahead and read our problem. So we can see that upon looking at these graphs, we can kind of estimate the velocity and acceleration. In the y direction, both of these balls will be released from rest. So this ball will be released from rest while this ball in the y direction is rolling off the table. So it never really starts with any initial velocity in the y direction at all. It has some velocity in the x direction, but not in the y direction. So because they both fall from the same height, so they have the same height, and they're both they're going to be accelerating at the same rate. So they're both being affected by gravity, 9.81 meters per second squared. And we can see here that they both have a curve for their y position. Okay, so both y positions are going to have the same graph. So let's look at our problem down here. So whenever we look at this problem, we know that since the balls have the same vertical position, we can relate it to our warm-up whenever there were people in trees, and in these trees we had people shooting some sort of bullet from the tree. So it actually had to depend on the height at which the person was on the tree, okay, for us to determine how long it would take for the bullet to reach the ground. So the letter would be D. And we can also see that if the graphs show us the same thing, that these balls at this point in time will reach the floor, we can verify that as our answer. So question number 3 shows us the same thing. Let's go down to question number 3. So suppose that experiment 1 and 2 are conducted at the same time. So it's just reiterating the question. The question is, what is the acceleration of the center of mass of the two-ball system relative to Earth? So our system is going to be one ball being dropped from rest, another ball being rolled off the table. So essentially, these two balls are going to be one system. So this red square is going to be one system. What's not included in our system is going to be Earth. Okay, so this is Earth. So what do we know about Earth? Earth provides gravity. And if Earth provides gravity, then the acceleration that these balls will exhibit is going to be equal to equal to G, which is letter B. Yes, wonderful. Okay, let's go on to number 4. A student is provided with a battery-powered car, and the manufacturer claims that it will operate at a constant speed. The student must design an experiment to test the claim. Which of the tools can the student use to test the validity of the claim? So your answers are going to be A and B. So the photo gates will be placed at the beginning and end. So in our experiment, whenever we use photo gates, we found that whenever we use a photo gate, it can give us the velocity of an object. So that's what we need. We need constant speed. We never really use multiple photo gates in one path, but if we were to do this, then we would be able to find at various distances the amount of time that passes between these distances. So velocity is going to be reliant on distance over time, so these photo gates will record the distance traveled in between that time. And B shows a meter stick, and of course we always use a meter stick to measure distance. Velocity relies on distance, so therefore it's going to be B. So an object undergoes an acceleration as it travels along a horizontal section of a track. So plain Jane car traveling. It has an acceleration that is not zero. So if we know that this acceleration is non-zero, therefore there is going to be a changing velocity. Just like if we had an acceleration that is equal to 0, velocity would be constant. But in this case, velocity is going to be changing. So graphically, because eventually this problem is going to make us look at a graph, we have acceleration in time. Acceleration is going to be some sort of acceleration. It's going to be constant. So if it's constant, and let's say that it's going to be positive, that means our velocity graph is going to have to be changing in the positive direction. So if we were to look back at our instantaneous points on a line, okay, instantaneous points on a line, and our instantaneous points on a line will give us the instantaneous slope. We know that the instantaneous slope of a line gives us acceleration. So we know acceleration is going to be positive here, and acceleration is going to be positive, 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 and it's going to be at the same rate this whole time. Okay? So from here, we know that since velocity is changing, we also know that position would also be changing. So if a car is going to be starting from a small speed and it increases its speed, of course its position is not going to change at a constant rate. It's going to be changing at more of a different kind of an exponential rate. So it's going to be more like this, right? So it's going to be exponential. And since it's going to be exponential, we can verify the instantaneous slopes. So we know that the instantaneous slopes along here will give us velocity, instantaneous. So slope will give us velocity. So you know that the tangent slope is going to be positive velocity. It's going to be increasing, increasing, increasing. It's going to get really big, so it's going to get more positive, right? So these are going to be the general graphs that we see. So let's see what we got. So we're looking at these graphs, and I see got speed. So that looks like that's one of my answers. And I can already tell you the second answer is going to be D. So the second answer is going to be D. Oh, nope, it's going to be C. So position and time squared. We didn't really go over that graph, and I already know my other graphs do not match any of the graphs that I made. But looking at C, C would match my graphs only because of the time squared. So time squared will come in because of linearization. So linearization, remember, it's going to affect the way that we graph. So it's going to affect the way that we graph. And since it affects the way that we graph, we're going to get a linear line. So we know an equation that includes acceleration in it is going to be our UAM equations. So our UAM equations, let's look at that. We know that a UAM equation that has position and time in it is going to be x naught, velocity 1/2 of acceleration times squared. So this equation has not only time squared in it, but it also has position. So let's modify this little equation so that it can look more graph friendly. So we can say the change in position, which would be, so change in position is going to be equal to v naught t plus 1/2 of at squared. Didn't really do much there, but it's going to be just like y equals a squared plus b. Kind of like the equation y equals a squared plus bx plus c. Wait, this is going to be bx, right? So linearization will make us put y on the y-axis. So in this case, position is on the y-axis, and then acceleration, so the entire acceleration, oh wait, sorry, not acceleration, a on the x-axis, so t squared will be on the x-axis. Looks like a jumbled up mess, but we will eventually get a straight line. A car initially at rest accelerates at 10 meters per second. The car's speed after it has traveled 25 meters is most nearly. So the car's speed, that's velocity, after it's traveled, so that's going to be our final velocity. So that is our final velocity. 10 meters per second is acceleration. 25 meters is going to be our change in position. So we have, we're going to assume that our initial position was 0 and our final position is 25. So 25 minus 0 is going to be our change in position. Okay. So let's set up our toolbox. So change in position is being 25, v naught. So the car is initially at rest. So since the car is initially at rest, 0 meters per second. V is what we're looking for. Acceleration is 10, and we are not given time at all. So we're not given time, and we're not given velocity. So that makes this choice really easy. So our immediate equation should be v squared equals v squared naught plus 2 times acceleration times the change in position, because this equation does not have time in it. So this equation does not have time. So from here we know that v naught is going to be 0, so it's going to be cancel out to 0, 2 times acceleration, which is 10, change in x, which is 20. So v squared is going to be, so v is going to be equal to, whenever you algebraically do it, it's going to be 22.3 meters per second, most likely close to c. Going on to the next question, we have that a student drops a rock from the top of a cliff such that the rock falls downward towards the Earth's surface in the absence of air resistance. The downward direction is considered to be the positive direction. The graph shows the rock's velocity as a function of time. Which of the following methods could be used to determine the total distance traveled by the rock after 4 seconds? So we're going to try to find a method. So right off the bat, I can tell I'm given a velocity versus time graph. So if I'm given a velocity versus time graph, I know that if I find the slope of this graph, it'll give me acceleration. If I find the area under the curve, then that'll give me position. Okay, so let's see what I'm trying to look for in the question. So the question wants us to say, it wants us to determine the total distance traveled by the rock after 4 seconds. So it's asking distance from us. If it's asking distance for us, then we can look for something about area in our answer. So if we want to find area in their answer, I can see already area here, and then therefore that's my answer. Bada bing, bada boom. Okay, ignore that. Future Evie, cut that out, please. Okay, never mind. It's left in. Okay, let's move on. Going on to this next problem here, we see identical objects X and Y held by a string, and they're on an incline. If they're on the incline, they get released. And when they get released, the center of mass of the system has its own velocity. So this center of mass is going to be described by this little point that we see here. And then the question states that if we have a new situation where the string was cut, so we're going to cut the string, and if we cut the string, then we know that object Y is going to be the one where object Y will fall to the bottom. Okay, so this is our new situation. So if object Y falls to the bottom, then we have a new center of mass. So originally, if we let this whole two-system uncut system fall down the incline, the center of mass will end up being like right over here. So the original center of mass travels from here to here in this certain amount of time. So let's say it's 4 seconds. Okay, so this new situation where this is going to be in red, where object X and object Y will separate from each other, but they're still one system. So if they're one system, they have a center of mass. So if object X and object Y have a center of mass, and I'm just going to put it directly in the middle of it, its center of mass will only travel from here to here. So in the same amount of time, the second situation will cover less distance in the same amount of time. So in the same amount of time, it's covering less distance over time. So it will be going obviously slower than the first situation. So if it's going slower, therefore its acceleration is going to be less. Okay, so in our new situation than the original. So then that means our answer will be A, new will be less than original. And I'm just going to show that down here. Letter B. Okay, so number 9. Number 9, we have a velocity versus time graph. So remember that velocity versus time graphs gives us, for the slope gives us acceleration, and the area gives us position. Okay, position. So knowing that, we see that we need to find the correct description. So if we want to look at letter A, the magnitude of acceleration for object 2 is greater than the magnitude of acceleration for object 1. So we know that if we find slope of these two these two lines, we're going to find acceleration. But we can see that they have the same slope in the same magnitude and slope, but it's going to be different directions. So whatever acceleration is going to be here, it's going to be negative, and then we have a positive acceleration, but it's all the same, so that's incorrect. Letter B says, after 2 seconds, object 1 travels a greater distance than object 2. So let's see here. Object 1 in 2 seconds is going to travel this entire area bound by its curve. So you can see that it's a nice little trapezoid. But in object 2 scenario, object 2 will only travel this much. Right, so we can see that object 2's distance traveled is going to be less than object 1. Okay, so change in position is going to be the area bound by the curve. So I can stand by that. So it's going to be B. I already know it's B. So object 1 and 2 in letter C are at the same horizontal position at 2 seconds. That's not going to be true, because we know that object 1 is going to start out like zooming out of the gate at 40 meters per second. So it's going to be covering a lot of distance, right? And then object 2 is going to be starting from rest. So there's no way it's going to catch up to the distance or meet in the middle with object 1. And we also know they travel different distances, so it can't be letter C. Letter D says after 4 seconds, the speed of object 1 is greater than the speed of object 2. And if you can just read this graph, we know obviously object 2 is going to be the one that has a greater speed. So it can't be D. All right, going on to number 10. Number 10 gives us yet another velocity versus time graph. So at time t equals 0, a moving cart on a horizontal track is at a position of 0.5 meters. Using a motion detector, students generate a velocity time graph. And at 2.5 seconds, the car's position is most nearly. So they're trying to find a final position. And we find that its initial position is going to be 0.5. So we know that if we have a velocity time graph, we find the area under the curve. That's going to give us change in position. So change in position, what does that mean? So change in position is going to give us final position minus initial position. So final minus initial. Well, bound by this curve in 2.5 seconds, we can see, and I'm going to highlight it here, we have a area underneath the curve, and then we have a area above the curve. So I highlighted them in different colors. So whenever you find the areas of the curve, we know that this side is going to be positive and this side's going to be negative. So let's do the first one. So the first one, I'm just going to label it triangle 1 and triangle 2. So triangle 1 is going to be equal to the area equals 1/2 of base times height. That is the area of a triangle. So we know that 1/2 of the base of the triangle, which is 1.5 seconds. Right over here, 1.5 seconds over times 3 meters per second. So that's going to be it in velocity. So if we know this, then we know that the area is going to be 2.25 meters. So 2.25 meters is going to be the change in position. So for triangle number 2, the change in position is going to be, whenever we set up the equation, it's going to be 1/2 of whatever the base is, and the base is going to be 1 second times a -2 meters per second. So that's why it ends up being negative. So if it ends up being negative, then we're going to have negative 1.0 meters as our change in position. So now we're going to add both of those up. So whenever we add 2.25 minus 1.0, we get 1.25, and that's actually going to be our change in position for real this time. Okay. So we know that change in position is going to be 1.25. We also know that our initial position is going to be 0.5, and we're trying to solve for final position. So if we're trying to solve for final position, we algebra it, and our answer is going to be 1.75, letter C. Number 11 is a really easy one. An object is sliding to the right along a straight line on a horizontal surface. The graph shows the object's velocity as a function of time. What is the object's displacement? Remember, displacement is going to have a positive and a negative or a negative associated with it. So again, if we find the area under the curve, we're going to find our change in position, or my displacement. So let's look at this. These triangles look pretty even to me. So that means our displacement is going to be 0 because they look pretty even, so they cancel each other out. So we can also look at this intuitively, where we have this velocity, so it's going to be, this object is traveling along this line at a large velocity, and it's going to be going in the positive direction. So we have this line, this object is going to be going in the positive direction really fast, and then it's going to be slowing down, and then at some point it's going to be changing directions and moving in the negative direction back to where it came from, right? So wherever it's 0, so our displacement is 0, letter A. Number 12 is an easy one as well. An object is dropped from the top of a building at Earth's surface. After 2 seconds, a second object is thrown. After the 4 seconds, the first object strikes the ground. What is the approximate acceleration of the center of mass of the two object system? So there goes our system talk again. So we know that this first object travels down, and it's going to get to this point before this next object is going to be thrown, and it's going to get to that point. So we know that since it's going to be falling off a building, we know it's affected by acceleration. And I can already guess that since it's in free fall, acceleration is going to be somewhere around 9.81 meters per second squared. But no matter where these objects are, so this ball is down there, it's almost going to fall to the ground, it's still being affected by the same acceleration as this other block. So we're talking about a two ball system. So I'm going to circle this and call this my system. So as a whole, my system can be represented by a dot. At what acceleration will it travel at? Well, you know that both of these balls will be traveling at the same acceleration of about 10 meters per second squared. So then as a whole, the system is traveling an acceleration of 10 meters per second squared. And we can also verify that on the graph where these have the same slope. So you can even calculate the slope and you'll get 10 meters per second squared. And they will be the same. Okay, number 13 looks difficult, but it's really not that bad. So whenever we look at these blocks are going to be traveling on ice. So if it's traveling on ice, therefore there's not really going to be much friction. So friction is going to be a no-go. So their direction of travel is in this direction. And since even though these blocks are going to be traveling in a circle, their center of mass is right here. So as a whole, the center of mass travels from here to here. Okay? So it's going to be translational. So not spinning in willy-nilly circles, just in one directional motion. So we also have a graph, and luckily this is a velocity time graph. We've mastered that by now. We know that slope is going to be equal to acceleration and area is going to be equal to position. Let's look at our question. So these two blocks are tied together with a string. They're thrown onto a layer of ice such that they spin around and they slide horizontally. A graph of the two-block system, so let's highlight that, the two-block system. So that two-block system, that's going to be all one system. Based on the graph, which of the following claims are correct? Select two answers. So let's look at what we got here. So the total displacement of an individual block is 0 because it travels in a perfect circle around the center of mass of the system. Although that is true that it does travel in a perfect circle and it ends up where it started from, our system is going to be focused on that two-block system that circles around a center of mass. So the system as a whole will only be traveling in one direction horizontally. So that's not going to be true. The acceleration of the center of mass of the system is constant. Well, if we look at the graph and we see our velocity time graph, we have our velocity time graph's slope to be a constant instantaneous slope. So the instantaneous slope is going to be a constant acceleration. So we see acceleration is going to be negative because the slope is going to be negative. So our tangent instantaneous slopes is going to be negative. So that's probably true, and it is true. So that's for B. Letter C, the change of velocity per unit time for the system center of mass changes as time increases. So velocity per unit of time is just another way to say acceleration. We already state that acceleration is constant, so there's no way that can be true. Therefore, D is our answer. The system's acceleration vector is opposite to the direction of the system's velocity vector. So that's just saying since velocity goes one direction, acceleration is going to go the opposite direction, and that is absolutely true. Let's look at this in the picture format. So if we look at the picture format, we know that since the object is going to be traveling in one direction, so it's traveling in one direction, and we know that since it's traveling in this direction, and since the object isn't speeding up, it's actually due to the looks of the graph. Due to the looks of the graph, the velocity is going to be decreasing. So if the velocity is decreasing, then acceleration is going to be negative. Acceleration is going to be working against that velocity in order to decrease the velocity going on. So velocity will end up being really, 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 really small, and acceleration is going to start to grow, okay, until it reaches whatever point it is at. That concludes the videos for the kinematics unit of this midterm review. Check out the next video for the dynamics part of the midterm review. Bye!